Hi everyone, I'm Dr. Mondazir from the School of Modeling, Simulation, and Training. In this video, we're going to explore correlation, linear regression, and then get into some meta-analysis, all looking at a data set that's built inside R. In this video, we're going to explore how we can do this kind of analysis using this programming language so you can do it at home, or in a lab, or anywhere. This data set that we're using is something that is built in, so you don't have to download the data set specifically. But if you do want to incorporate your own data, you can easily do that just by replacing the data set we'll be using. We're going to be using something called Posit Cloud. It's a cloud-based service that allows you to code R or Python on the cloud. It has a nice user interface for its integrated development environment, IDE, where you'd be typing in code, running code, and then seeing the output. The nice thing is, once you have a system and account set up, you will always have access to your code as long as you have access to the internet. I'm using Posit Cloud here. There's a free tier for it with some minimal number of hours that you can use per month. If you have RStudio running on your own computer, you don't have to worry about that, and you can still follow along with this. I'll make the R notebook that I'm going to be using available to you. If you want to upload it to Posit, Jupyter, or Google Colab, just know that this notebook that we'll be using is compatible if you're going to run it locally or if you're going to be running it on a cloud service. Let's jump in. If you're using Posit Cloud, go to Posit Cloud, log in if you already have an account or you're going to sign up. The good thing is if you have a Gmail account or Google account, you can use that, log in, and it'll take you to the environment and you can start coding straight away. I've already created an account. I already have notebooks. I have projects going on. Once you log in, yours is probably going to be empty, but if you have existing projects, you'll see your projects here. Just because I have mine, that's why you see some things already listed. We're going to be creating a new project, and I'm going to load my notebook and show you the steps to load yours. We'll jump into the analysis we're doing in this video. Once you're logged in, you'll see something like this. Just go ahead and click New Project. You're going to see something that says New RStudio Project. Go ahead and click that. It's going to then deploy your project. This means it's just going to create a space for you on Posit's cloud service. Once it's done loading, you'll see our notebook, or actually an R environment that you see just like here. And we will then create a notebook and set up our environment. I'm providing you with this code. Unless you want to type it out, which you can with the code and the notebook, you'll be uploading it. So from here, you're going to go where it says upload, and then you're going to click this choose file option there to find the file that you'll be downloading I'm providing you. So click that. It'll then load the notebook. If you're not going to be using the notebook that I'm providing, you're going to go to File, New File, and then you should see our notebook. And that'll create a brand new notebook for you. Let's load this up. We're going to click yes. Let's go ahead and install some of these. Okay, that took a little while. So now that it's done installing, you should see something like this. This is your notebook where you're going to be typing in your code. Where it says plot, you just replace that with the code that you'll be following. You can kind of minimize this a little bit, and then you just be adding your own cells. I suggest that you upload the notebook that I shared. That way things will be faster, and then you can edit the code yourself. I'm going to jump into my existing notebook here, and then you'll see on the bottom right where it says files. When you have uploaded the file that I am providing, you're going to go ahead and click this. It says mtcars analysis. Just click that, and that will load the notebook that you see right here. So now that our code is set up, it's on posit.cloud, you've uploaded it, and now you should be able to see the code that you see in front of you. It may look a little bit like this, where this part, the console is a little bit larger. Go ahead and just minimize it or reduce it completely. Also, if you're unfamiliar with RStudio, you should notice that on the right, there's an environment. This is showing us the variables of our environment right now. I'm going to close this over. On the left, we have some menus. If you wanted to create a new workspace to do whatever code you want to, you can jump in and have some examples and stuff like that, some help right there. I'm going to go ahead and close this because I want to have as much real estate as I possibly can. So now we're going to be working in the environment that you see here. This video, or what we're going through now, is I'm going to talk to you how we're going to perform some correlation, some regression, and some meta-analysis on a data set that I have already, you're going to acquire too through the code that we're going to be using. If you don't want to type it out, that's fine. I provided the notebook that you can use, or you can follow along just to see what it's like to do the analysis that we're going to be doing. The analysis that we're going to be doing in this video could be translated to any kind of analysis that you have quantifiable data for. That means data that has numbers. If you want to understand the correlation between any of your variables, want to build a linear regression model to predict things, and do meta-analysis to extend the analysis. Maybe you're collecting several different kinds of studies together and you want to do some analysis on all of them to see if there's effect or not. All of this will be done here through code, but you can follow along without it. What you're seeing here is a notebook, and then we have code that I'm going to be executing. Please execute this code with me too. You can change any of this. The main thing is I want you to have a hands-on experience by actually building some of these models and doing some of the analysis that we're going to be covering in this video. So in this notebook, we're going to be exploring a data set called mtcars that has entries of car. We're going to look to see if there's a correlation between a car's weight and a car's miles per gallon. And then we're going to build a regression, a prediction model here that's going to be predicting when we have a car's weight, what is going to be its miles per gallon. You may be saying, oh, I know the car's weight does not have a relationship, or we cannot build a good model, or maybe yes, it's the opposite. In this video, we're going to be exploring all of this. And then at the end, we're going to do some meta-analysis to see if there's an effect across multiple independent experiments. Does the weight actually affect a car's miles per gallon? So it's a very simple thing, but you can import your own data. You can do the analysis on your own data as you will. Right, so let's get into this. I'm assuming that you're familiar with R. We're not going to cover the basics of R, but you have code to perform this analysis. So none of this should be new to you, but if it is, just review some R. The first thing I'm doing here is installing my R required packages, and I'm going to be using ggplot to graph some things. I suggest you use ggplot too, because ggplot is a nice way to have some aesthetically beautiful graphs pretty quickly and easily. Then we're going to be using knitr, and knitr allows us to create a HTML file of this. So if you wanted to have a report, you can use knitr and share that HTML file. Anybody on the internet or anywhere can open up the analysis that you've done, and they don't need to know anything about R, any bit of coding. And then we're also going to be using a library called metaphor. Metaphor is for meta-analysis, and we're going to be doing that at the very end. If I bring this up just a little bit, you see that we have a terminal here. This terminal goes into all the code stuff. So as we're running, if we see any errors will pop up in this terminal, in this window that we have here. We have the console. We're not going to be using this terminal. We're mostly using the console. If you had any errors, just look at the console. We're going to run this one at a time. I've already ran some of these, so you can go ahead and run. And the way you run it is in a cell or in a chunk. You're going to see this little play button over here. Just run that. Just press that once. That should load the code that you have here. The first thing we're doing is we're going to install the libraries that we need to develop the analysis. I've already done this, so we just assume that I've ran it. Then I'm going to run knitr. Knitr is going to set up my environment, and then I'm going to load my libraries. Loading the libraries allows us to use things such as ggplot and knitr. In this case, we're going to be using this to perform our analysis, first using some data analytics, and then to generate that HTML file I mentioned before. So I'm going to execute this, and you just hit the run button, and it loads the libraries that we need. And next thing is we're going to load the data set. We're going to be using a data set that's already built into R, especially if you're using something like ggplot. It's called mtcars. mtcars has data on cars. So we're going to load this data to have it. It would change. You see in the top right here, the environment that we have for our environment. It will update mtcars, and then it just loads up the value up there. So now we have imported our data set. Now it's time to preview our data set. Our data set has a lot of rows in it, but you can preview the first 10 rows of data by doing head and then passing in mtcars there. When you run this cell, you get a preview of the cars in this data set. This data set has more rows, more car entries than this. I just used head just so we can see. But let's just play around with this a little bit. I'm going to take out head, and I'm going to put it back once we're done. But I'm going to take out head. I type in mtcars, and I hit play. And you see that there's 32 rows of data. So we have 32 rows or 32 instances of data that we've collected data on cars. So you see that we have the cars listed here. We have some Mazdas. We have a Hornet. We have 2 Hornets. We have some vehicle information that we have here. We also have columns of data. This is one of the columns that we'll be focused on, MPGs, miles per gallon. We also have another column, WT, for weight. We're going to really focus on these 2 columns here. We're going to be using this to see if there's a relationship between the weight of a vehicle and the miles per gallon. So maybe the heavier car you have, the less miles you get per gallon. Or vice versa. Maybe if you have a super heavy car, you're going to get better miles per gallon. We're exploring this in this video. But you can also see that we have other columns such as cylinder, displacement, the number of gears, etc. So this is a preview of our data set. If I type back head and I pass in my parameter of our data set, we now have just a preview of our data. This is not cutting our data or anything. It's just so we can see a little bit of our data. And it's going to look pretty nice in our HTML file that we can use knitter later on. Okay, so scrolling down, continuing, I have this cell here, which is splitting our data into training and testing sets. If you've never built a model before, it's important to have training and testing sets. You train your model on one set of data, and then you evaluate, you test your model on another set. This way you keep the integrity of your model, but you also have a fair way of saying how good your model is at the end. We train our model on some training data, and that training data is isolated from what we're going to be evaluating our model on. In this case, we're going to build our model on 75% of the car data, and then the other 25% we're going to use as testing. We're going to set that aside and see how good the model is on data that the model was not trained on. We're separating these here. What we're doing here is we're setting a seed. The seed just is used for reproducibility. It's so you and I can see the same output. If we set the seed here, when I do randomization, particularly when I'm collecting samples from our full data set of 32 cars, the random sampling, by setting it to 1, 2, 3, my set of rows for my training set and my testing set are going to be the same as yours, as long as we set the seed and follow this. Okay, so you're going to just run this. It will divide up our overall data from mtcars here, and it's going to split it up into two sets, our training set and our testing set. Next, it's good practice to visualize your data. We don't know too much about it. Let's say we went ahead and we collected some data. We just got back from the field. We want to collect some data. We've already collected data. We want to see what the data looks like. It's a good idea before doing analysis to throw it into some kind of visualization. This would allow you to see if there's some kind of relationship visually. Sometimes we intuitively have a good sense of identifying whether or not there's a relationship in data just by looking at it. Computers don't really have that right now, and we're getting better every day with this. But in the meantime, let's just throw this into a visualization. And this code here that I'm showing is I'm using ggplot to plot our training sets data. I want to keep our testing set data isolated for later on, but we're going to be looking at building stuff, evaluating stuff on our training data. We've collected data in the field. For one instance, we collected this data. And our testing set is maybe we collected a little bit later on, but we're going to evaluate what we think is the insights that we got later on our testing set. So we're keeping these things independent. And our ggplot is only going to be on our training set. So when we plot, we're looking at identifying some kind of relationship between the weight and the miles per gallon of a car. So let's go ahead and throw this in a plot where our X is our weight and our Y is our miles per gallon. Do you see a relationship between the weight and the miles per gallon? Is something clear, something obvious? Maybe you've detected something very quickly that a visualization of the data we imported is a little bit clearer than if we just looked at this data raw. Particularly if we looked at miles per gallon, the numbers, and the weights that we have here raw, it may be hard to identify if there's a relationship just by looking at the numbers. But through data visualization, this scatter plot, we're able to see that there's a relationship. As the weight of a car increases, what's happening with the miles per gallon? Do you see that there is a negative drop as the weight increases? There is a drop in the miles per gallon. Maybe we can use this to identify some kind of model to predict when we have a weight, what the miles per gallon is going to be. But let's just look at this visualization, and visually, at least I see a relationship. That leads us to correlation. And what I've added, and I've downloaded this from the internet, and I left this link here so you can see this image. Correlation is the relationship between at least two variables. As one variable goes up, what happens to the other variable? As one variable goes down, what happens to the other variable? Let's look at this image a little bit closer. As one value goes up, if the other value goes up, So if our x goes up and our y goes up, we say that there's a perfect positive correlation. When one value increases and the other value increases, we say that there's a positive correlation. It can be split between, if it always goes up, we say that it's high. And if it goes up, not every time, but maybe a good amount of the time, we say that there's a positive correlation. The same thing goes with negative correlation. As a value decreases, what happens to the other one? If a value decreases and the other value increases, then we can say that there's a negative correlation. And then like the categories we had before, we can say negative correlation is low, high, and perfect. We can also look at the values in between. If a value is a positive 1, that's the perfect score for correlation. That means every time one value goes up, the other value goes up. And then every time a value decreases and the other value increases, that's a perfect negative correlation. So it'll be -1. In the middle, 0 means there's no correlation. There's no relationship as one value increases that the other value does anything. There is no relationship between the x and the y variables. Here's a breakdown of our correlation values, and you can use these for your own analyses. If you're looking at two quantitative values, a x and a y, if you want to find out there's a relationship, we can use something called the Pearson correlation to identify how strong or weak or no correlation there is. So when we're talking about correlation, we're just saying as one increases, what happens to the other one? Continuing, Pearson correlation is a quantifiable way we can measure these values. And the Pearson correlation, you can see the values here underneath each of these graphs. We have a +1, a -1, and it ranges. The Pearson correlation quantifiably ranges. So if we wanted to look to see what's the relationship between MPG and weight, well, we can use the Pearson correlation to give us that value. In this case, we have a -0.859. A pretty strong negative correlation, as we're seeing over here. The closer that we're getting to -1, it's a stronger negative correlation because we're looking at weights and miles per gallon. As the weight increases, the miles per gallon of the car decreases. Let's go up a little bit. We saw this in this visualization. As the weight increased, we see that the trend is that the miles per gallon decreases. This is negative correlation. And our Pearson correlation value here is saying the same thing. As we've seen up here, a higher negative correlation is we're getting closer to -1. The further away from 0, +1, the stronger the negative correlation is. In this case, it's -0.859. So we can say that there's a relationship between weight and miles per gallon. It just happens to be as the weight is increasing, the miles per gallon is decreasing. There's a relationship, and we have quantifiable evidence from our study, from our training set. We can use that. If you wanted to explore other variables, we can use something called a correlation matrix to explain the relationship between any of the variables that we have here to one another. But if we wanted to find what other variables, what other columns have a relationship with miles per gallon, in this matrix, we could just look across. Here's miles per gallon. Let's just look across here. So we're looking at these values. Cylinder has a negative correlation. Displacement has a negative correlation. HP, horsepower, negative correlation. Let's see, are there any that have positive? Well, yes. This one here has a positive correlation of 0.69. That means as one value increases, there tends to be a positive increase in the other one. We also have the same thing for BS, for AM, for gear. Gear is a little bit less, right? Gear is 0.4. 0.4 is not a strong positive correlation. It'll be more of a weak or a low positive correlation of 0.4. We can look for other variables that have this quantifiable relationship between miles per gallon and anything else. But we're really focused on seeing if the relationship between miles per gallon and weight. Because we've identified that there is a correlation, which means that there is a linear relationship between the weight and the miles per gallon, we can use something called linear regression to make a prediction. If I scroll up to this graph again, here we're seeing a trend. And by looking at this, we may say that if we, based off our intuition, we can start seeing if there's a relationship between the data. And we just established through correlation that there's a quantifiable way that we can measure this. But you may estimate, what if the weight was right here, 4.5. Let's say in between, based off of thousands of pounds, right here, you can kind of estimate that the miles per gallon would be around here. You would be able to estimate, you looking at this and you seeing the relationship here. But we want to create some kind of data model that would be able to identify and predict when a value is anywhere on the spectrum, based off of the data that we have collected, based off the ranges, where would the miles per gallon fall under? We may have data for this weight here. We may have value for this weight here, but there's massive gaps here, maybe some here, like maybe 2.5. I already mentioned 4.5. What would be the miles per gallon at any of these weights that we don't see dots on? So that's where linear regression could come in. What we're doing is creating a model that's going to create a line, because linear regression, hopefully through these points, and that line would give us a good estimate of when we know what our x is, what our y is going to be. We actually want to create a function that looks like this. You've seen this before. X equals ax plus b. You've seen this in maybe high school, maybe as early as middle school. X equals ax plus b. This gives us this line here. Remember, we have slopes, we have y-intercepts. We want to create the function that would allow us to draw this line based off of the data that we've collected. And the way we can do this is through regression, particularly with linear regression, if there's a linear relationship with the data. Because we just established through correlation that there's a linear relationship as weight increases, the MPG decreases. Let's create a function that's going to give us this line. Once we have this function, we can predict based off of any weight what the MPG is going to be. The last thing I want to mention is this line here. We have these points. We want to generate a line that's going to give us the minimal error. Error is the difference between our line here, based off of these x's, and then any point that we have data from. We want to minimize the distance between this line and any point. We want to have it as perfect as possible. From a prediction standpoint, as we're training this, we want to make sure that our prediction has the lowest error at any x when we can give it a y. And then the last thing with this image is we're trying to identify the slope. So if you remember rise over run for our line, we also want to identify the y-intercept. That's where our line begins on the y-axis. Once we have this, we can create a function that's going to create this line for us. Then we have a prediction model. Our function is going to look like this. Y equals ax plus b, written in a different way. We have y, what we're trying to predict. We have that y-intercept. We have the value of x, which in this case will be our weight value, and y will be our miles per gallon. And then we want to find out what the slope and our y-intercept is of this function. Once we have an x, we can identify our y. We'll have a formula that would allow us to estimate what y is when given x. So the main part of our linear equation here is our slope coefficient and our y-intercept. Once we have this, any x that we have, we'll be able to predict its y. There's always going to be some kind of error unless you create the perfect function, perfect model for this. There's going to be some error. We want to reduce the error between all of these points and make sure our model is as good as possible. So that allows us to explore something called univariate linear regression. Univariate linear regression is a method of prediction that allows us to build a data model on data that has a linear relationship between our y that we're trying to predict and our x value that we're given. In this case, we're trying to create a line that has these values here that we can then say this is the lowest error that we can possibly generate. Again, it needs to have a strong linear relationship, and the way we do that is through correlation. In R, it's very easy to do this. We do LM, which we're going to create a linear model We pass in our y, in this case it's miles per gallon, this is what we want to predict, when given our weight, our x. And our data that we're building this model on is our training set. Remember, we have a training set, we have a testing set. I'm going to just print out our summary. This is going to show us what our coefficients are. And then lastly, I'm going to print out what the formula for our line that we have generated up here. We're going to print out what this formula looks like. So I ran it. This is the output, our summary. Most importantly, it outputs a couple of statistics, such as the residual standard error, our R squared, and our F statistic. That these three allow us to determine how good our model is, especially based off of the data that was given. And it also gives us our coefficient for our weight and our y-intercept here. We can take these two values, this value here for our y-intercept and our coefficient, and we can throw that into our formula. And our formula that we're given is this. Here's our y, miles per gallon. Here is our x, our weight. This is the slope. And then this is the y-intercept. We can then take this formula and we're able to generate this formula here. We're able to generate a line. In this case, if we graph it, this is our prediction line. So this model, our linear model, was able to give us this formula that allows us to predict our y when given our x. And when we graph it using ggplot, it allows us to see what that line looks like. So when I wanted to find out the value of 4.5, I can just go here, 4.5, and go up. And then see where it intersects on this line, and then go across. Here, it's about 2.7, 2.8 over miles per gallon. We can do this for any value that we have our x. Go 4, go up, and see where it intercepts. Same thing for 3, etc. We now have a predictive model that's based off of our training data. We're able to predict any y given our x. The next thing we need to do is determine how good our model is. And as I mentioned, we have something called error. There's really 3 types of error that you should be looking at when you're building any kind of regression formula, and they are MAE, our mean absolute error, mean squared error, and our root mean squared error, RMSE. These 3 values allow us to know what the between our line and any of the points we want to evaluate our model on the testing set we set aside. And now we're going to evaluate how good our model is on data that it hasn't seen before. We call predict, which allows us to estimate what values are predicted when we're given a certain x. We call predict on our model that we just created. Our new data is going to be our testing set. This would allow us to get a whole collection of predictions based off of our testing set. So we're basically passing in, these are weights you haven't seen. Give us the prediction for each of these weights. Then we're going to calculate residuals, MAE, MSE, and RMSE, and output them. Now we see what the error is for each of our testing sets weights. From here, we can compare. If we had another model, or if we had another possibility, let's say another feature, another X, another column that we wanted to look at, maybe cylinders, maybe displacement, we'd be able to compare how good our model is at predicting the MPG versus any of these other models. Maybe you've collected data from another experiment that's also looking at predicting the MPG from completely different cars, or maybe the same cars that came off at different times, different years, etc. From this, we're able to evaluate how good our model is. The lower the error, the better. So if you produce another model, you get the MAE, and you can compare it to this MAE. If yours has, or this other new model has a lower error, then that's the one to go with. We want to select a model that has the lowest error possible. We looked at our data. We saw that there is a negative trend. As our weight increases, MPG also decreased. We also got a quantifiable way of doing that through the Pearson correlation. Then we established that there is a linear relationship with our data. And then we created a univariate linear regression model to predict these values. Once we're given our weight, we want to identify what the MPG is, and we're able to do that and create a line for it. Now we have a function that we can always use. You can even do this calculation by hand. Once you have the formula, you go and easily plot it if you wanted to. Now that we have it, we were able to establish what the error is to say how good these models are. The next thing, because we've gone through all of this, we had a data set that we've collected. Maybe it was a data set that was collected last week and we want to perform this analysis, and we said, okay, this analysis is pretty good, but I'm interested in collecting more data and seeing if there's a effect of having weight try to predict the MPG. Does that scale across all cars? Does that scale across all times that this data is being collected? We'd be using data meta-analysis to perform this kind of analysis to see if the conclusions that we're able to draw from this model actually scales to other independent studies. So we're going to pretend, if we're going to do this, we're going to pretend that we have collected data from independent experiments. Let's say we wanted to collect data on cars that have 4 cylinders, or 6 cylinders, or 8 cylinders. We want to see the importance of weight when predicting MPG. Does this assessment scale? Does it actually translate when we're looking at another type of analysis? In this case, let's pretend that this is an independent study. We're asking if the number of cylinders still holds up to conclusions we made that weight does have an effect on predicting miles per gallon. This allows us to perform meta-analysis. Okay, so in meta-analysis that we're doing here is we're going to subset our data into our 4 cylinder cases. We're going to build models for each of these. I have a model for 4 cylinders, 6 cylinders, and 8 cylinders. I just created 4 predictive models, 3 more predictive models to add to the original. Again, we're looking at this and we pass in maybe all the data that we collected from these independent studies. We create a linear model, and this would allow us to look at the effect size. So in this case, we're getting the slopes, the coefficients, getting the standard errors for all of these, and we're collecting this to start performing meta-analysis. The very first thing we do after that is we're going to look at the effect size. That's why we're doing this. We're putting this in a data frame that allows us to look at this meta-analysis. Now we can start performing the meta-analysis. And we're going to look at the random effects meta-analysis, especially on these coefficients that we're given. So we're taking the coefficients that we have and putting this in this function to get our meta-analysis results, and we're going to print out the summary. The main thing is we want to assess how good these models are, especially when we're looking at weight to predict the MPG. The very first one we have here is the log likelihood. This allows us to determine the fitness of the model. In this case, the higher or the less negative our values are, that indicates a better fit model. That indicates how strong our conclusions were before of weights to MPG, how it translates now that we're looking at cylinders, broken down into cylinders. We also have deviance, which is outputted. This is also showing the goodness of fit. This allows us to look at making more conclusions based off of the log likelihood that we have here. Let's see how things scale, if things still hold up. The lower value here, it indicates the better fit the model is. So if we had 2 models or 2 assessments, we're looking to see a decrease in deviance. This is showing us how good our model is. We also have other values such as AIC, BIC, and AICC. These values also support, they're just different kinds. Like one is based off of a Bayesian information criteria. And then the next values that we see here are tau and H. They're showing us the heterogeneity of our statistics, of our assessments. Heterogeneity is really showing us as our data is changing, especially when we're looking at things like the different cylinders, we can see how it translates, how much importance our values that we have looked at, including our weight going to MPG, how it translates into strength. Are we seeing the same conclusions as before, where weight has more importance in predicting our MPG? We have tau, we have H. These values identify the heterogeneity of these. And then we have the significance. We have Q statistics for heterogeneity. We have p-values showing the significance in our effect sizes. I've added some conclusions. The random effects of the model, they suggest that there is a significant negative effect size that we have here, and that means that our outcome decreases significantly as our weight increases. So we're seeing that there's a connection. We're seeing that there's more of a relationship that is translating as we've gone through different kinds of cylinders as our independent tests. We're getting more support for this. We also have that p-value, the p-value that we have right here. It's showing us that because it's very low, it indicates that there's a strong level of evidence that we saw our observed effect. We saw that it still holds. That weight among our three different cylinders still has a good importance in predicting our MPG. So with these values, and you can look at even more, have even more conclusions that we have here that you can translate. And I'm also giving you a forest plot that shows us the significance as the cylinders increased. You can print these out. You can have these included in your analysis to say that whether or not, as we went from one independent experiment to another, if the same conclusions held. Now we have quantifiable methods such as those p-values, our confidence intervals, our heterogeneity values based off of the tau and our h values, how they, our I and our h values, how they translate. We have quantifiable methods to say that our conclusions that we saw before, not only did we generate a linear regression function that's based off of our training set, but when we looked at independent tests, that we broke it down into cylinders, so we had 4, 6, and 8, the same conclusions could be made. When predicting our weight, we'd be able to predict our MPG. This allows us to do some meta-analysis to say, okay, if we had multiple studies together, do the studies all lead to the same conclusions? Just to recap, in this video, we covered how to import data, mostly using posit.cloud to get you started. We imported our data. Once we import our data, we looked at our data, did some data visualizations, and then used a quantifiable measure to output the correlation, the relationship between two variables. We covered the Pearson correlation. Then we looked at actually creating a model. In this case, we created a data model called linear regression. We used that to produce the line, our model line, to predict when given a value of X, what that value of Y is. In this case, we use weight, because we realized that a strong correlation between weight and the miles per gallon. We created a model here. Then we calculated what the error was, and we can use this to evaluate how good this model is versus another model. For example, we have models created based off cylinders. We generated the errors for each of these. We can compare it to our original error. And remember that we split our data between our training and testing set, and we only evaluated it on our testing set. This is data that we did not train our model on. And then lastly, we got into meta-analysis. We created those independent studies, we brought them together, and we were able to perform meta-analysis in a quantifiable way by looking at values such as the log likelihood, deviance, tau for heterogeneity, etc. And now we're able to say that our conclusions before that weight can be used to predict MPG across multiple studies. Now we have additional support for that. That's it for this video. Thank you for your time. Now you have this code. Please go ahead and run it yourself. And I suggest you play around with the values. Take care.